What's an angle?
A measurement of a degree.
A measurement of a degree. Degree is one of the units we use to measure angles, but that's not what an angle is.
A section of 360
Not necessarily. Do you know an angle if you see one? So what's it look like?
An edge.
Looks like that. All right, basically. So an angle has two, what are those called? They're not lines because they are only half of a line. What's half a line called? These are called rays. So a half a line is called a ray. So you have two rays. Yeah, we learned this back in 6th grade. That's correct. So we have two rays that have the same initial point. That's called the initial point where they meet right there. And typically we have one side is called the initial side. And one side is called the terminal side. And this rotation here in between the two rays, that's called the angle. There are two different systems. Actually, there's three different systems, but we're only going to do two in this class. There are two different systems that we are going to use to measure angles. What are the two systems called? Somebody already mentioned one of them today. Give to the D. Degrees. And the other is radians. Now, for our purposes, when we draw an angle, traditionally, one of the sides will be the positive x-axis. So we're always going to measure angles from the positive side of the x-axis. If we measure a degree, if we measure an angle this way, if we measure it counterclockwise, we consider that to be a positive angle. On the other hand, if we measure it clockwise, we consider that to be negative. So notice this angle, I could measure it two different ways. I could measure it as a positive angle. I could measure it as a negative angle. Clockwise is negative. So here's a funny question I had somebody ask me a year ago when I taught this course. What are you going to do when all clocks are digital? And you can't say clockwise and counterclockwise anymore.
You'll just have to know what they mean, I guess.
Yeah.
Without the context. Except for the fact that it would be considered digital, so it's
Still be around. My answer was I'll use the little circle on internet searches that spins around and around. The internet search one way and the internet search the other way. Anyway, fortunately I still have a clock in this room and it goes clockwise. We can use clockwise and counterclockwise. Alright, so we have two different systems, radians and degrees. What's the third system? Anybody know the third system? Starts with a G. Gradians is correct. Gradians is the third system. It sounds like radians, but it's pronounced gradient. You actually see gradients in your life once in a great while. If you're driving around in a mountainous area, you might see trucks use low gear, 20% grade. What does 20% grade mean? Is 20% of what? 20% of 90 degrees. So in gradients, this angle right here in gradients is called 100%. That's the gradient measure. We will not use gradients, correct? But that's what it is. Gradients is just a percent system. So a 90-degree angle is considered 100%, 100 gradients. And so a 20% grade is 20% of 90 degrees. That's an excellent question. I don't know.
The truckers know a lot about things.
Yes. They know when they have to put their truck in low gear so they don't go flying down the hill and crash. Yes. They know that. All right, so that's great. Radians. Let's talk about radians for a minute. How much is 1 radian? Anybody draw me 1 radian? Pi over 3 is usually a radian measure, but that's not 1 radian. It's not too far off from 1 though, because pi is about 3.14. So 3.14 over 3, that's pretty close to 1. So pi over 3 is pretty close to 1 radian, but it's not 1 radian. No, pi isn't 1. Pi is 2.14 approximately. Pi over pi. All right, so here's the circle. Sort of. That's a circle. And this circle has a radius of, it doesn't really matter. I'm going to call this radius r. The definition of 1 radian is I take that length r and I wrap it around the circle. So I draw an arc length. I draw an arc length that's exactly the same as the radius. So if I had brought a piece of string with me, I could have used the string to draw a circle, and then I could have laid the string out on the arc and made those the same exact distance. That angle right there is 1 radian. When the radius equals the arc length, that's the definition of 1 radian. Now, in this class, we've actually been using radians a lot. We just didn't call them radians up to this point. What I mean by that is, if I draw a unit circle, radius equals 1. And I asked you, what's this arc length right here?
No, pi over 2.
That arc length is pi over 2. Since the circle has a radius 1, what's that angle? It would be 90 degrees, but I want the answer in radians. I'll give you a hint. The answer is written up there. The angle measurement right there, that angle is pi over 2 radians. When you're dealing with a circle of radius 1, the arc length and the radians are exactly the same. So, what's the arc length for going all the way around a circle of radius 1? 2 pi. So what's the angle for going all the way around a circle?
2 radians.
In radians, it is 2 pi. So angle for 1 complete revolution is 2 pi radians. Very soon we're going to talk about trigonometry in terms of triangles. So we'll redefine sine and cosine using triangles all the time instead of unit circles. Very soon. Like the very next section, I think, section 6.2, I think we talk about triangles. All right, so that's radians. So we've been using radians all along, we just didn't call them that. So anytime I ask you about pi over 3, back in chapter 5 we were calling that an arc length. Pi over 3 is also the equivalent radian measure of the angle that you get. And then we had things like 5 pi over 6 and negative 3 pi over 2. All those arc lengths that we were dealing with are exactly the same as the radian measure. So we've been using radians from day one, we just never called it that.
So radians impact
Correct. Yes. So for example, I could draw this angle right here, where this angle might be 2 pi over 3. Yes, eventually we will be doing arc and cosines to find the angles. We'll be doing all that stuff. Yeah, we'll get to that. All right, how about degrees? Can anybody draw 1 degree for me?
And 98 of the first one.
All right, so most of you are very familiar with degrees. So this angle right here is called 90 degrees. So 1 degree would be 1/90th of that angle. So 1 degree is very, very, very tiny, isn't it? Something like that maybe would be 1 degree. It's difficult to draw 1 degree exactly. It's actually pretty easy to draw 1 radian exactly. All right, and then something important that we will use here in a few minutes. That angle right there, that's 180 degrees. What is it in radians? Pi, because it's halfway around the circle. The arc length would be pi. That's pi radians. All right, so onto this worksheet that I passed out. The symbol for radians that's commonly used is nothing. So normally we would write 180 degrees equals pi. And if there's no symbol there, it's assumed that it's in radians. So you have to write a degree symbol if you're working in degrees. If you're working in radians, you just get to write the number. So sometimes you will see some people write a little r just to be very, very clear. But typically there's no symbol written if you're working in degrees, if you're working in radians. All right, so how do I take 100 degrees and convert it to radians?
It's either
Correct. It's one or the other. It's either 180 over pi or pi over 180. Which way does it go?
I think you have to do I think that's to like cancel out.
Exactly. What you want to do is you want to cancel out units. So we're going to multiply this by pi over 180. Because then I have degrees on top and I have degrees on bottom, the units reduce out. So I really just have to take my fraction and reduce what's 100 divided by 180 when you reduce. It's 10 over, okay, so you reduce first by 10, it's 10 over 18, and then you reduce by 2. You're right, 5/9. So it would be 5 pi over 9. So 100 degrees would be the same as 5 pi over 9 radians. How about negative 70 degrees? Well, we do the exact same thing. We multiply it by pi over 180 degrees. So what's 70 divided by 180? Negative 7 pi over 18, reduced by 10. All right, so if I start with degrees and I want radians, I multiply by pi over 180. What if I go the other way? What if I start with radians, like 5 pi over 6, and I want to convert it to degrees? 180 over pi. So now I have 180 degrees on top, pi radians on bottom. The radians cancel with the radians, and I'm left with degrees. Well, it also works out nice because that pi reduces with that pi. What's 5 times 180 divided by 6? It's 150 degrees. Okay, negative 13 pi over 12, same deal. I multiply it by 180 degrees over pi radians. And again, the pi's reduce out. How much? Negative 195 degrees. You could use 360. If you use 360, then what do you have to use in radians? 2 pi. So you might as well reduce the fraction from the beginning. Instead of using 360 over 2 pi, you might as well cancel out the 2's and use 180 over pi. Would it be wrong to use 360 over 2 pi? Of course not. I could also use 90 degrees over pi over 2. It's just harder because then I got more fractions to deal with. So we typically use 180 over pi because it's reduced and it's easiest. All right, determine 2 coterminal angles, one positive and one negative. What are coterminal angles?
Angles that are the same except in different quadrants.
Not the same, but in different quadrants.
Well, like you have 90 degrees up, you have 90 degrees down. Well, mirror images.
No. Correct. When I drew this, I drew coterminal angles. I can measure this angle positive, or I can measure it negative, and those are considered coterminal. I could also do this. I could go all the way around the circle one time, and then go to there. And I still have the same terminal segment. That's why they're called coterminal. Okay. So if I give you an angle like 340 degrees, how are you going to find a coterminal angle? I can subtract 360. So 340 minus 360 degrees is negative 20 degrees. So there's one correct answer, and that one's a negative angle. And how could I find a positive one? Add 360, add one complete rotation. So another correct answer is 340 degrees plus 360 degrees. Somebody said 700 degrees. All right, so there's the answer for part A. Subtract 360, add 360. That gives you coterminal angles. How about if I'm working in radians? I have to add 2 pi and I have to subtract 2 pi because 2 pi is one complete revolution. So I have to take 5 pi over 8 and add 2 pi.
You could also just convert it to degrees. Convert it back.
Yes, you could convert it to degrees and then add 360 and then convert it back. That seems like more work than necessary. I would just do it this way to begin with. I would write it as 5 pi over 8 plus 2 pi. 2 pi is 16 pi over 8. Just get a common denominator and add. So that's going to be 21 pi over 8. And conversely, 2 pi over 8 minus 2 pi is 5 pi over 8 minus 16 pi over 8, which is? I got negative 11. That's because I'm right? Oh, okay. All right, so there's my coterminal angles. All right, find the area of a sector of the circle. Okay, we need a couple more formulas here. Dr. Gauges. If you have a circle, boy, I didn't draw those very straight. That ever. If you have a circle, and this circle has a radius of r, and you have an angle, theta. Typically Greek letters are used for angles, angle theta. Then this arc length, the distance from here to here, the arc length is given by a formula. This arc length is called S. S equals r theta. Now, the only rule here is the important rule. This only works when theta is measured in radians, not degrees. In order for this arc length formula to work, you must use radians. Always, always, always must use radians. And then the other formula is the area of the sector. What do I mean by area of the sector? What would the area of the sector be in the picture? Yeah, it would be the area in between the two rays there. So it would be the area of that chunk of the circle. Area is 1/2 r squared theta. And again, you must use radians. Okay, so to answer number 4, determine the area of the sector of the circle with radius 8 and central angle 80 degrees. Well, the formula I just gave you was area is 1/2 r squared theta. So that's going to be 1/2 times 8 squared times, and then what's the problem? They gave me 80 degrees, and I just told you can't use degrees, you have to use radians. So you have to convert it. So it's going to be 80 degrees times pi over 180 degrees. You absolutely, positively have to convert it. At this point, what I would probably do is grab my calculator. And this is 1/2 times 8 squared times 80 divided by 180. So, a correct answer is 128 pi over 9. How did I get that? I did 1/2 times 8 squared times 80 divided by 180. And I didn't mess with the pi at all, so I just dealt with all the nice numbers, and then at the end I threw a pi on it.
Let's see, I got 14.
I got 14.222 repeating over and over again?
Yeah, I did not.
And then I did math frac, yeah, to get 128 over 9. My guess is when you go to do your homework on WebAssign, my guess is they're going to want the exact answer like that. But read the directions. If they ask for a decimal approximation, of course you can type that in and get a decimal also. Okay. Let's skip down to number 6. We'll come back to number 5 in a minute here. Number 6. The top and bottom ends of a windshield wiper blade are 34 inches and 14 inches respectively from the pivot point. While in operation, the wiper sweeps through 135 degrees. Determine the area swept by the blade. So basically what I'm saying is, you've got your windshield wiper blade, you've got 14 inches here, and then you've got 34 more inches there. And then when it sweeps, you're getting a chunk like that that clears your windshield wiper, that clears your windshield. This first 14 inches, that's just to get it out up on the windshield here. That part's not actually wiping away the water and dirt on the windshield there. Just this part is. So we want to know that area. So you probably wondered about that every time you drove down the road and turned on your windshield wiper blades. How much area is that clearing out for me? Right?
Not enough, because there's always something.
Yeah, and there's always some on the edges too where it doesn't clear your windshield. It doesn't wipe the whole windshield, right? Well, how much area does it clear? Well, how would you figure that out? All right, first off, we're giving a degree measure, so we'll need to convert that to radians. That's true. How are you going to figure out the area of this thing? Any ideas? Find the area of both? What do you mean the area of both? So you mean find the whole area, and then find the green area and subtract them. That's exactly right. So your answer is going to be the area is 1/2. What's the big radius? It's 48 because it's 14 plus 34, isn't it? So the big area, the entire area of the thing, has a radius of 48 squared times 135 degrees, but we need to convert that to radians. And then we subtract the area that we don't get cleaned off, which is this area down here. So that's 1/2 times 14 squared times 135 degrees times pi over 180 degrees. All right, so again, I would grab my calculator. 1/2 times 48 squared times 135 over 180 minus 1/2 times 14 squared times 135 over 180. I guess I'll leave it. That's a decimal. I got 790.5 pi square inches. So I did it all in once. I took the 0.5 times 48 squared times 135 over 180, and then minus the 0.5 times 14 squared times 135 over 180. So I did all the arithmetic at once except for the pi's. Threw a pi on the end. To the left?
No.
Oh, so
No, yeah.
okay. I got 790.5 times pi. You got that too? All right. Inches squared would be your units. Yep, square inches. All right. Next. I need a computer picture here. Going back to this video. Watch the little gear. And watch the time. One revolution, 2 revolutions. How long does it take that little gear to make 2 revolutions?
2 seconds.
It's actually 3 seconds, I think, if you watch carefully. 1, 2. Well, I guess it is 4 seconds. The video runs for 5 seconds. That's what was confusing me. Okay, so for the little gear, what's its angular speed? It did how many rotations? 2, which is what angle? 1 revolution would be 2 pi, so 2 revolutions would be 4 pi. So its angular speed is 4 pi divided by, how long did it take? 4 seconds. So its angular speed would be pi, and the units would be radians per second. Now again, watching the video, what can you tell me about the big gear? It did 1 revolution in 4 seconds. So its angular speed would be 2 pi over 4, which is pi over 2 radians per second. So they have different angular speeds. They're spinning at different speeds, aren't they? And you can see that clearly. The little gear is going twice as fast as the big gear. Now, what's linear speed? Anybody know what linear speed means? If I were to drop that gear on the floor and let it roll, how far would it roll in over this time? So linear speed is circumference over time. Okay, so these 2 gears that we have. What's the radius of the first gear? Half of that of the big gear. So let's make up a number for the radius of the small gear. 2. And the radius of the big gear is then 4. Okay, so little gear, we're going to say it has a radius of 2. And the big gear is twice as big. So we're going to say its radius is 4. Big gear, little gear. Okay, so what's the linear speed of the little gear? Well, it did 2 revolutions in 4 seconds, correct? So if that thing were laying on the floor and it did 2 revolutions, how far would it roll? The exact same amount as the big gear. That's what we're going to find out in a minute here. That's correct. Their linear speeds are the same because they're connected. But if it went 1 revolution, how far would it roll? I want an exact number. Back to the picture here. If it goes 1 revolution,
2 pi. Is it the period?
if it goes 1 revolution, how far would it roll as its circumference, isn't it? The distance it rolls, if it started right here and if this were on the ground, it would roll that far, 1 complete circle, which is its circumference. So the little gear with a radius of 2, what's its circumference? How do you find circumference of a circle? 2 pi r. So its circumference would be 2 pi times its radius, which would be 2. Except it made 2 revolutions, didn't it? So if it made 2 revolutions, it then it went how far? 2 circumferences, correct? So there's 1 revolution, there's 2 revolutions, and that took 4 seconds. So that's 2 times 2 times 2, that's 8 over 4. That sounds like it's about 2 pi. And I'm guessing these were in inches. So that's 2 pi inches per second. On the other hand, what's the linear speed of the big gear? Well, it only did 1 revolution. So what was its circumference? 2 pi times 4, and it took 4 seconds. So those 2 gears, because they are connected, they have exactly the same linear speed. If I put them on the floor and let them roll, they're going to go at exactly the same speed. But they had different angular speeds because of different sizes.
So technically, if you have 2 cars going the same speed and one has a larger tire, the car with a larger tire will go up.
No, if they're going the same speed, if you have 2 cars, one has a small tire, one has a big tire, and they're going the same speed, they're going to be running right next to each other. But what's happening is the car with the little wheel has to be spinning faster. The car with the little wheel is going to have a bigger angular speed, but they're going to have exactly the same linear speed because they're going the same speed. All right, so we will come back on Wednesday and we'll look at problems 7 and 8. Problems 7 and 8 deal with linear speed and angular speed. See you Wednesday.